so you want to replenish that.
Excuse me, do you mind if I start preparing my...
Oh, I'm sorry.
No problem.
Where are you going?
There's a class in here right now.
Oh, there is?
Yeah.
Oh. What? Which one should? Laptop one. Okay. Oh, what happened? Okay. All right. So let me do some recap from the last time. So last time we talked about the problem called maximum concurrent flow, which is a problem that generalized max flow problem, like single demand flow problem, and we also talk about like let's say that this thing MCF is the maximum concurrent flow for H concurrent flow. So now I also have defined this thing, kind of the order with respect to flow between two graphs. Can someone recall what is the meaning of this? Like,
Is able to satisfy every demand demanded by H.
right, exactly. So there exists concurrent flow, a feasible concurrent flow where the demand is H in G. In other words, we say H is embeddable into G or is routable in G. Okay. And And how does this thing, how can you write it in terms of this order?
The maximum tau such that tau into h is still available.
Right, max tau such that after you scale tau by, like scale h by tau, then you can embed it into G. Yeah. You ask for the maximum scale where you can embed it into G. Okay, so that is just some recap. And we have seen that max flow in the multi-commodity sense is similar to like min cut in the multi-commodity sense within log n factor. So that is a good thing to know. In other words, if there is a sparse cut in H, then the H concurrent flow must be small. And if there is no sparse cut, you will find large flow as well, but maybe within log n factor. Okay. Okay, so that is to recap. And by the way, so we talk about this order here, and actually it is like a kind of nice way to think about how to compare like well connectivity between graph, right? If G is at least H is like more connected than H, you can embed H into G. But this is kind of with respect to flow. Actually, now we want to talk about another way to order the graph, and it basically is have a connection to like a H expansion. So let me just define it. So again, let's say that you have graph H and G that are capacitated graph, and I will just say that H is cutwise at most G if for every cut in the graph, the cut size in the total capacity or the weight of the cut in H is just at most the weight of the same cut in G. Right? So you have two graphs H and G, and look at any set S, then the cut size in H here is like less than the cut size in G. This thing is smaller than this thing. Okay. And if this is true for every cut, then we say that H is at like cutwise at most G. Okay. And you can see that really just by definition, it means that if H is less than G, then the H expansion of G is at least 1. This is really just by definition. And like the way to think about this is, again, like if we say that H is less than G if there is no sparse cut in G with respect to H. Okay. And you can recall this notation where I can scale, like I can talk about like add a graph and scale the graph by some constant. And you can see, like you can verify by yourself that this order between graph in the cut sense, you have a partial order, like everything that should hold does hold. It is transitive. If you have G1 is less than G2 and G2 is less than G3, then G1 is less than G3. It's transitive. And if G1 is less than G2, and if you add both G1 and G2 by the same graph H, then this is still less than this one. So this is just like the definition of how to compare two graphs in cut sense. Okay. Now, this is just another way to, like, I just want to talk about like the relationship between how, like, this comparison based on cut and this comparison based on flow. So they are kind of, I want to say that they are basically kind of the same relationship. That is, if H is embeddable into G, or H is flow-wise at most G, then H will be at most G cut-wise too. So, but on the other hand, if H is less than G in cut-wise sense, then H will be less than G too, but with this log-n factor in flow sense. And actually, this is really the same thing as, it's the same statement. Actually, it's equivalent to approximate mean max flow mean cut. But let me just show you one direction that if you have max flow mean cut theorem, then this is indeed true. Why is that? So, okay. So just to recall the max flow mean cut theorem statement here, right? And also recall that by definition, if H is embeddable into G, then it's the same thing as saying that H max flow is at least 1. And if H is cut-wise less than G, or at most G, then H expansion of G is at least 1. Okay. So this is just to, you need to recall this. And now let's prove one direction, this one. Okay, so suppose that H is at most G, flow-wise. Then you have that maximum concurrent flow is at least 1. But because of this inequality, you have that H expansion is more than 1 too, which means that H is cut-wise at most G. On the other hand, yeah, kind of the same. Just do the math. All right, I will just skip. Yeah. Okay. So, okay, I keep repeating this. Yeah, basically, it means that if there is a like, if there is a sparse cut, like if you can embed the flow, then there cannot be any like sparse cut with respect to like, if you can embed H into G, you cannot have any sparse cut in G with respect to H. And if there is no sparse cut, you can embed it with log-n factor. This is just to repeat things again and again, but again, so like morally, what you should think about approximate max flow mean cut is that these two orders are kind of the same. It's kind of the same thing, the same way to compare graph, but if you ignore like log-n factor. Okay. And okay, yeah, right. I need some volunteer for scribing the last file here and this one. Any volunteer for this actually? Which one do you want?
The last one.
Okay, thanks. And how about this one? Okay, thanks a lot. Okay, so here we're gonna kind of like several lecture before is kind of so that I can talk about this one. It's really like the thing that important to me, I think, the way I think about expander. So let's see about this. Basically, it's a way to look at expander in flow perspective. So just to recall again, like from the first lecture, I said that any expander behave like a complete graph, and we see one perspective of expander that is robust. We saw like robustness view perspective of expander. And now we're gonna show how like expander behave like the most well-connected graph, like or complete graph, into more formal sense. Which is cut and flow. So okay, let's start with some terminology. So let D, think of D as like a function that assign number into vertices. Okay, and now we just said that the graph have degree profile D if basically the degree of every node U is assigned by the function D. Okay, and the graph is D restricted if the degree is like at most D on every node. And now the last thing is that we talk about the D product graph is the graph where you define the weight on every edge by this factor. Like you have seen this graph already actually. Yeah, if you have node U and V, then the edge is just like you multiply du by dv and scale it down by d of everything. Okay. So just for your intuition, suppose that d is 1 for all u. Then what is a product graph? Like, this is not a trick question. Just say, can you say that? Sorry? Not quite. Well,
Unweighted graph is scaled down by proportional.
unweighted graph. Can you say it again? Sorry.
Like everything has same weight and same capacity with the scaling down of 2m.
Yeah. So it's just kind of a complete graph because every edge, for every two nodes, you have an edge, right? And they have the same weight because the weight of every one is the same, but you scale down every edge by 1 over n. Oh yeah, D. I really like. D is like a number that you say you want, and so the way to think about product graph is like you think of complete graph, where you scale the weight such that the degree on every node U agree with the D function. Why is that? Like, so do you see this? That is in the D product graph. You really have that the degree profile of D product graph is D. So for all node U, degree of U here, you really like sum over all other node V, right? u dv over dv. But when you sum all this up, then it is 1, so you have dv. So you should think of the product graph as a complete graph. But you like kind of, but now instead of complete graph, like if D is like uniform, it's really like a complete graph where you scale everything by some constant. But now if D is not uniform, if D is not constant, then it's still kind of complete graph, but you scale things so that it the degree agree with the function D. Make sense? Yeah. It contains self-loop too. Yeah. Okay. So I just want to make it more formal that the product graph are really like well connected in the same sense that complete graph is well connected. So just recall these two ways to order the graph. One is cut-wise cut order, and another one is flow order. So, okay. What I want to say is that, okay, among all graphs that are D-restricted, that the degree is at most D on like, the degree is like respect this function D, then the D product graph is really the most well-connected one with respect to both cut and flow. Yeah. So, so like this is just the formal definition. Okay, every edge UV, you just put the weight of this. But morally, yeah, it's kind of complete graph when you scale things so that you have the degree profile to be D. All right, so let's prove this. Like that is this D product graph is like the most well connected one. So it will not be like exact, but at least what I will prove is that like every cut, like basically every cut in the product graph is almost maximally big. And in other words, if you compare, if you have any graph that is D-restricted, this graph is less than the product graph, okay? But maybe with a factor 2 here. Okay. But basically every graph is less than K. As long as they have degree which is D-restricted. Because if some graph is not D-restricted, it's not really like makes sense to compare them that much, because the guy that have degree much larger, there's no way that it's going to be smaller than K. Right? But as long as you look into this class of graph of D-restricted, K is the biggest one. So why is that? Well, this is really just we really just like look at the definition and you can see. So let's look at H and K here, right? And take any cut. Let's take any cut S, and let's say S is on the smaller side. Okay. So first of all, we know that the cut size here of H is going to be at most ds. Just because even the total volume here is at most ds, right? So the cut size is at most the volume, but this volume is at most ds. Okay. And now I'm gonna prove that if you look at the same cut in K, then the cut size here should be like at least ds over 2. If we have done that, then we are done, because within a factor of 2, every cut of K is more than the cut of H. But how do you compute that? Well, we know that we just kind of count all edges crossing K, right? But this look like there is no so it's kind of like a complete graph, but let's just compute it. So okay, this should be K. So what do we have? We have that let's look at this node U in S. Okay. How much is the weight from U going out to something outside S? That's what I want to count. And well, you're just summing up overall V outside the cut S. And then you have this thing, and this is going to be du of minus S over dV. Yeah, we assume that S is on the smaller side. Yeah. And we can always look at the smaller side of a cut, because given any cut, you just, if it's bigger on the bigger side, you just flip it. The cut side doesn't change, right? Yeah. Okay, so now this one, because S is on the smaller side, this thing is like at least half. So what does it say here? It says that if you look at U, more than half of its degree will go outside S. And now if you sum up over all nodes in U, that is going to be like sum up over all nodes in U, then you get the total cut size. Okay, this should be so many typo. Yeah. So if you count, like this is a cut size contributed by U, is at least the degree of U. Now if you count over all nodes, the cut size is going to be at least ds over 2. Because, like, make sense? Okay. Yeah. By the way, this is just the same thing as proving that for any restricted graph, D-restricted graph H, the H conductance of K is at least half. It's just really the same statement that we are doing here. Okay, so K is indeed the maximum guy with respect to cut within like a class of D-restricted graph. Let's say the same thing for how about flow. Okay, is K, like the product graph, the maximum guy as well? So let's try to prove that. Yes.
Here 2K is not D restricted, right?
Yeah, so 2k is not de-restricted.
But then we are saying k is the among the restricted k is like well.
Yeah, within a factor of 2. Yeah. We kind of, I can, like, I ignore that, yeah. Like, I compare h and k, and it is indeed less, h is indeed less than k if I give 2 factor to k. Yeah. Okay. All right. For flow, I'm gonna kind of say the same thing. That is, any de-restricted demand graph, like think of demand as h, and h define the demand. And if this demand is de-restricted, this graph is de-restricted, it's gonna be routable in G, in the product graph K2, within a factor of 2 again. Okay, that's what we're gonna show. So and I want to stress again that actually let me just go ahead to the proof. What I want to show is that for any restricted demand graph H, all of this, like this demand gonna be routable in K with congestion 2. That is here. H is less than 2K. So how do we show that H is like less than 2K? We need to construct the flow. Like we need to embed H into K with congestion 2. So I will just describe how to embed that. I will show you the H concurrent flow in K, right? And the way to do that is the following. Consider this H and this is K. And suppose just try to look at one demand in H. Okay. S and T. I just need to construct a flow for each of the demand. How does it look like? It's gonna look like that, look like this. So I gonna send it from S to V and then to T and do this for every V. I kind of exploit the fact that K is like a complete, there are like a complete connection between any node. So I really try to distribute this flow to everyone and then go to T. Okay, and how much? So let's say that, so let's look at just one node V here and call this, so this is a flow, let's call this flow path SVT. So the flow gonna look like this, right? Like everything here, but let's look at just one path right now. For each of these paths, how much should I send flow along this path? So, well, I'm gonna distribute it in the very natural way. So first of all of this, the value of flow on all of this should sum up to the size, to the value, like the demand from S to T. That is defined by the graph H here, right? That's the first thing we need to do. But how much should I distribute the flow on this path? Well, just for each node V, the flow path that I send through this one is going to be the fraction of like dV over d capital V times this thing, right? So indeed, you have that for this flow from S to T, the total flow will sum up to what you want. Okay. So this is really like, and I just do this simultaneously for every demand. This is just for one demand. If there is another demand, we're gonna do this like again and again. Like you have this thing over each other. Like the flow for every demand, you construct the flow for that demand and do this simultaneously. So that really embed H into K. Right. What we just need to say now is just that this flow is indeed a good one. It has small congestion. Question?
Does the capital V contain S and T?
Yeah. So
we have a direct path from S to T.
It has self-loop from S to S, then to T.
yeah. This graph have self loop too. So maybe think of you send from S to S and then to T.
Oh.
Yeah. All right.
The same then we have to do with S to T and then T to T as well.
Yeah. Right. Like it can be S to T and T to T, or S to S and S to T. Okay. So, but is the construction of the flow clear to you? All right. So now let's analyze the congestion. Well, if you want to analyze the congestion, you just need to look at each edge, right? And look at how much flow go through that edge. So let's say that you have a graph. This is graph K, and then there is this node UV. Okay. So when is it the case that you use this edge? Well, it's going to be used in many paths. But what path? So there are two types of paths that will use this edge. One is just when you have a source and you would like to send it to source from source S to V. It's going to look like this. And like the source, if you have the demand from S to V, it's going to send flow like through many guys to V, right? But one of the flow path will be the one that goes through U and then to V. And you just take this overall source. So it's going to be maybe S2 that sends something like this. And S3 sends something like that. So that is just one side. And then, well, symmetrically, you have when you have T, and you would like to send it to T. So something like this, T2, and so on. So that is really all the flow path that use this edge, UV. Right? So what is the total flow value that go through the edge? Then you just sum up over all this flow value. Yeah.
So I always see an inherent directionality in the edges which you are talking, but they're not imposing any direction direct. So in that case, why can't V be a source and you route it to VU and some other T1?
If V be a source, then if V is a source, then if we want to send flow to S, then it's gonna be this, right? So I mean, I really just look at the, I don't think of, so it's just that when, how should I say this? This is like, I said that this is source, but there is no direction. It's just like the demand between S and V. We can think of this as a V is a source that sends to S2. Yeah.
It's like U being a middle vertex and V being the middle vertex. Those are the two cases.
Yeah. But that is the two cases, U being the middle one and V being the middle one. Yeah, right.
And in that sense, we cover all the vertices, the other end of the. So it will not double.
Even if we double count, it will be like a factor of 2, and we don't care that much. But I don't know how to answer this. So,
I think.
is it okay? Yeah. Okay. Yeah. Question or? All right. You can ask if you. Yeah. All right. So these are just the two set of paths that we need to count the value, right? So let's just calculate. So how about this one? Is going to be this sum. So from S to V, the demand from S to V, the demand, I should say between S and V, is there is no S to V, it's between S and V. Yeah. Well, that goes, this demand that goes through you, how large is the flow? Well, it's always like this demand, right? Then you scale by U, by du over dv. Now you sum this thing over all S, because this is like summing over all S. You range over all S here. Well, what is that? Then it's gonna be like summing this thing over all S, which is the degree of V in H. And this is a factor here. This thing is a factor here. Make sense? And the same thing for T. Like you're summing up over all T for the demand between U and T with this scale. Then you have this thing. Like this sum is the degree of U in H. But H, but this thing is at most dV, and this is at most du. Why? Yeah, H is D restricted. And so it means like each of this then is just this. If you replace this thing by dV, then this is exactly the weight of an H in the graph, in the product graph. So you get that. All right, so congestion is at most 2. Okay. So keep this in mind. Product graph is the most well-connected one among all the restricted graph. Keep that in mind. Let's switch gear a bit and switch to expanders. At the end, I'm gonna say that it's not just product graph, but expander are the one that is the most well-connected one too. But to do that, we need to talk about second part here. So let's talk about expander. When you have an expander G, what if I want to prove that like G, like this expander is larger than H? G is or larger than H in flow or cut sense, right? How to argue about that? So we have seen like to prove this formally or like or exactly is not like it's gonna be maybe quite hard because to this thing maybe require you to compare between 2 to the n many cuts, and that is like hard to do. How about flow? You need to compute like multi-commodity flow. That is actually easier to do, but still maybe like complicated. Turns out that if you don't care much about, like if you are okay with some approximation, then just show that the degree of G is big enough. Then you can conclude something like that. Just look at the degree and you're done for expander. So what do I mean by that? So I will say that H is less than G degree-wise if the degree of G is at more than degree of H for every node. Okay, and now this is gonna be very simple but powerful. If G is an expander, and you just compare that the degree, and the degree of G is more than the degree of H for every node, then H is indeed less than G cut-wise, but with this factor, 1/5. So if phi is like, if you have very good expander, then indeed H is indeed less than G, like with constant factor. But if phi is like a small, if it's not really a good expander, then it doesn't say much here. Okay. But the conceptual message is quite strong here, right? Instead of look at all cuts, just look at n many degree cuts. Very simple thing to compute. So let's prove it. Well, take any cut. Like I'm gonna prove this, right? So let's take any cut S, which is on the smaller side. Okay. Okay. Take H. This is H, and this is G, and let's say S here is on the smaller side of G. Okay. Then we know that what do we know? The cut size here in H is going to be at most the volume of G, the volume of S in G. Why is that? Yeah, like the cut size is going to be at most the degree, the volume in the cut size in H is trivially at most the volume in H. But because H is less than G in degree, so the volume of the cut S in H is at most the volume in G. Make sense? So we have.
Are we assuming like unit capacity or something?
Volume and degree here, I really talk about the capacitated degree or like it's a weighted degree.
Oh, wait, okay.
Yeah,
Sorry.
yeah. Okay. Right. Yeah, this is really like a kappa of H in between you and everything outside you. Yeah. All right. So this thing is trivially at most the volume of G. But how large is this? How large is this cut in G?
Because of expander.
Yeah, it's an expander. So it's going to be at least phi of volume.
One more thing, what the KH is basically D of mu, D of G by D of capital.
Say it again.
The KH is again the product of KH.
KH. No, this is now at any graph. H is now any graph. So it's not a product of anything.
Then how capacity, how do we have it with respect to degree of H? What is the function?
I think we're defining the degree of H to be like the capacity, the sum of the capacity.
Oh,
Right.
That's what confused me.
Yeah. So yeah, the degree is a weighted degree. Yeah. Again, degree of H in U is the cut size around you, really. So it's a cut.
Is any general.
Yeah, kappa H is just any graph, and kappa H is just the capacity in graph H. But here I just say that like the cut size is at most the total capacity, total volume inside H, inside the cut. This is what you have, and because of this, you have that this is the case. This is at most this. Okay. Okay, so on one hand you have that the cut in H is at most the volume in G of the volume here, but the cut in G is at least phi times the volume. So it just means that the cut in H is at most 1/5 times the cut in G. And this is true for every cut. So you have this. The reason that this is true is you should think of, if you have expander, then the cut the cut size in expander is kind of almost maximally big anyway. So it's gonna be bigger than any cut, like compared to other graph which is still de-restricted or like which have the same kind of degree. Then the cut in G is gonna be kind of almost bigger. All right. So now, immediately, we can say the same thing for flow. That is, if G is an expander, H is any graph which is like half degree, its degree is smaller than G, then H is gonna be at most log n over phi times G. H is gonna be embeddable into G. And why is that? This is because of the Maxwell mean cut theorem, right? Like this thing and this thing are kind of the same up to log n factor. So if H is at most G with this factor, H is gonna be like at most in cut way, H is gonna be embeddable into G too with the same factor, but with additional log n factor. Okay. All right, so that's what we have. We have that if you want to compare, like to say that G is bigger than H in cut or flow sense, but if G is an expander, just if the degree is big enough, then you're done. All right. Okay. So now.
Degree is big enough and G has to be expanded as well.
No. If degree is big enough, think like this dumbbell graph, right? The degree is like this is complete graph, this is complete graph. Every node have big degree, but it's not an expander. Okay. So if the degree of G is big enough, it doesn't mean that G it must be an expander.
Yeah, but for it to be, so what was the theorem you mentioned?
I'm just saying that if you have any graph and G is an expander, and if degree of G is big enough than H, then not just that the degree is big enough, but H is gonna be, the whole H is gonna be embeddable into G. Yeah.
But,
And every cut of H is gonna be like at most that cut in G too. For every cut, not just degree cut.
yeah.
Yeah.
Yeah, I was just telling G needs to be pi expander, right? G has to be pi expander, then only this will be true.
Yeah. Yeah, I assume that G is an expander. All right. Just some more definition. So we have seen that how to compare two graphs in cut sense and in flow sense. And I just want to just would like to introduce the notion of equivalent in cut and flow sense, which is just that I said that G1 and G2 is alpha cut equivalent if there exists alpha 1 and alpha 2 such that like when you multiply them, this is less than alpha, and G2 is at most alpha 1 times G1, and G1 is at most alpha 2 times G2. This might look a bit confusing, but if you think of everything as one, like if alpha is 1, alpha 1 is 1, alpha 2 is 1, then it just means that all cuts are the same. If this is less than G2 and this is less than G1, then it means that for every cut, they have the same cut size. But the definition is such that it kind of really just measure how close the cut between G1 and G2 is, but modulo some scaling. What do I mean by that? If you just take G1 to be some graph and G2 to be the same as G1, but you scale it by 100, then they will be still equivalent with this definition. Why? Like it will still be one equivalent, which is exactly the same. Why? Because like G2 will be at most 100 times G1, but G1 is at most 1 over 100 times G2, and 100 times this thing is going to be still 1. So if alpha is small, the smaller alpha is, then they are like the cut size are almost the same for every cut, except that you allow some scaling. Like,
Can't you get, like, can't you just make one of the constants big enough and always get one?
make one of the constant big enough.
I don't know if my question is.
So
One take out. Out. Yeah, right? Is that you just
It's the both graph are like kind of like structured differently. And some cuts maybe.
So let's look at an example. Yeah. So like if you have maybe like one graph is a dumbbell, and another graph is a complete graph. So maybe first you find a scaling such that the degree is the same, right? So that like at least this cut are the same thing as this cut. So now the degree are the same. But once you fix such that the degree is like choose a scaling such that the degree on each node is the same, then you're gonna see that like if you compare between these two cuts, it's gonna be very different. Yeah. All right. And I can just define the same thing for flow by replacing like cut by flow here, right? I said that G1 and G2 is alpha flow equivalent if they exist alpha 1 and alpha 2, where these two things hold. Okay. So exercise for you now. If they are like, if G1 and G2 is like alpha flow equivalent, why is it the case that G1 and G2 must be alpha cut equivalent? Why is that?
Log n will cancel out.
There will be no log n actually. Yeah. So just actually there is no canceling too. The thing is just that we have seen that if H is less than G in flow sense, then H is less than cut, less than G in cut sense. This is no factor that we lose. But another direction here, you lose a log n factor. So flow is kind of slightly stronger than cut. If you have that H is embeddable into G, then in flow sense, then H is at most G in cut sense. It's like this thing is a bit stronger. Flow is a bit stronger. Okay. But yeah, if you have that, this is true for cut, it's true for flow too, but with log n factor, and that's why you lose log square factor here. Right. Okay, now I'm gonna conclude a lot of things here. We have every ingredient that we need now. So we will say that first, basically I'm gonna say that if you have an expander with the same degree profile, then they are basically approximately the same for both flow and cut sense. Like they are both cut equivalent and flow equivalent. Just need to compare the degree. So basically, if you have G and G prime to be phi expanders with degree profile D that have the same degree profile, why this is true? Yeah, yeah. Previously, we showed that like if not just G, but if it's just any graph H, which is the restricted and have degree at most G prime, then you would have that it would be less cutwise than G prime 2 by 1/5, like with 1/5 factor here. But now they really have the same degree, so you can conclude this too, and you have other direction is just symmetric, right? Like they are really symmetric here, and with this, you just conclude that they are G and G prime are cut equivalent with 1/5 square factor. How do you get this?
Because of the previous case.
Right, because you have that if you have relation of cut, you get the same relation for flow with log n factor. So you have this, and it's symmetric. You have both direction here, so they are flow equivalent with this factor. Okay. So basically, and note by the way that I don't really need that they have exactly the same degree profile, right? If the degree profile are kind of similar within some factor, I'm gonna just lose some that factor here or there. So this is like it's kind of robust statement. You don't need it to be the same degree profile. Okay. So that's the first thing to know. Kind of expander with the same degree profile kind of form an equivalent class. They have the same cut and flow structure really. Although there are so many expander out there, they are kind of the same from cut and flow perspective. Now, note that they would be equivalent to the D product graph too. Why? Because the D product graph is an expander, and it has degree profile D. Right. So in this equivalent class, the product graph is in that class. But what do we know about product graph? It's the most well-connected one. So maybe I should jump into here. Like this is a picture that you should have in mind. Like suppose that this is all class of all graph that is D restricted. Then D product graph is like the one that is the most well-connected one is on the top. But and you have a set of expander here that have the degree profile D. This thing kind of you form the equivalent class, and the D product graph is in here. And this equivalent class are like the most well-connected class, the most well-connected one within all of this D restricted graph. Does it make sense? Okay. Yeah.
has any relation to the partial order of cut and flow, or it doesn't?
So equivalence just mean, I mean this equivalent.
Alpha equivalent.
Yeah.
It doesn't mean that they both can't be compared in cut sense or flow sense. Like the partial order thing is totally different from this equivalent.
No. I really mean by equivalent. I really means about this partial order here. I mean that they are kind of these are instead of there's within some factor log n or log square. They are kind of this if you have anything in the class, if you have G1 and G2 in the same class, then you will have this less than G1 less than G2 and G2 also less than G1, but maybe with some log factor. Yeah.
So then G1 is called G1 is equivalent to G2, ignoring the factors.
Yeah, so this is here, right? So is alpha equivalent if kind of ignore some factor, then they are the same. Yeah, and by equivalent here I mean like it's kind of log square or over phi equivalent with flow and cut. All right, and actually, if you just compare between like any expander and like here I just compare between any two expander, but if you really compare between one expander and one product graph, then you have a bit better factor when you compare them, because I have shown that for one direction you have just a factor of 2. Yeah, like k is really a bigger than everything with a factor of 2. For another direction, this is just from before. So you have kind of instead of square here, you don't have a square. Okay. So k. Any expander and the product graph is equivalent with this factor. Okay. And this is conceptually quite nice because as you see, like product graph is a kind of a complete graph. It has so large, so many edges, like so many weighted edges. And expander, you can have, it can be weighted, but you can have just linearly many edges. If you just count the number of edges, they might be much smaller, but it's still as good as a product graph. Like they are equivalent. Yeah.
Sorry, Patrick. Can I ask a dumb question? It goes back to Harry's question. Like, if in your corollary, could you put G as at most cut of 2/5k?
You can put this.
Yeah, because phi would typically, it's less than 1, right? So
Yeah.
Scaling it up. So then, like, when you multiply these things together, you are sort of full 1 cutting. Oh, never mind. Yeah.
So yeah, this thing
No, I understand now.
imply.
I'm stupid. Never.
Yeah. Anyway, all right. Don't worry. Yeah, yeah. Thanks for.
So another question.
Yeah.
So like, are there any like relation between phi and d? Is there not,
No. So
it can be quite like arbitrary.
So for any D, and for any D there exists a phi expander. So there is no relation. Yeah.
So can we think of two different parameters?
Yeah, really two different things. Yeah. Okay. So now we just have that, like I just repeat here. that, okay, we have shown that, we have shown before that for all the restricted graph, H is at most 2K. But now this you just can replace the product graph by any expander. It's the most well-connected one. If you are okay with paying this 105 factor. All right. And now, last thing. Suppose that you don't know if, suppose that you want to show that some graph G prime, which is the restricted, is kind of, you want to show that they are in the good class, the cool guy here. Yeah. Like you have some G prime here. If you want to show that they are in this well-connected class, one thing you can show is just, if you can show that K is actually less than G prime, then obviously this guy must be in this class, right? But you will see later that, we just see now that actually it's fine. You don't need to really show that K is less than G prime. If you can show that for any expander G here, if G is less than G prime, then it's as good. G will be in this well-connected class too. Yeah. So like, just to say it again, if G is any expander with degree profile D, and G is any, G prime is any graph which is the restricted. If you can embed G, the expander, once you can embed any expander into some graph, immediately that graph is the most well-connected guy. And okay, then G prime will be like more than any edge for every restricted edge. Yeah. And this is what I mean by like, it means what? It means that if I want to ask you for some certificate, like I want to say that G prime is the most well-connected guy. What is the certificate for that? Give me any multi-community flow that embed any expander into G prime, then G prime is good. The certificate for like goodness, for well-connected, is just some flow that embed any expander into the graph. Okay. So that is just kind of everything. Now, you can just read the summary here, I think. So, because I don't have much time, I want to talk about the right way to think about expander. Last thing for today. So you have G is an expander. If G has uniform degree, then you have that G is kind of equivalent to the product graph, but but this product graph, when you have uniform degree, the product graph is just the complete graph, right? If G is has uniform degree, G is equivalent to complete graph. And that is like a nice thing that you can picture about. But if it doesn't have uniform degree, it's equivalent to this product graph. It's kind of a bit awkward to think about. I don't like that. It's actually much more convenient to think about expander in the following way. So, and suppose that the graph is unweighted for now, because otherwise you can just add parallel edges. think of the graph is like you have unweighted graph, and you have G. You have G, and what I'm gonna do is just let's look at another graph G prime that can be obtained from G. Okay, where you just subdivide each edge. UV here. You just add another node. You can call it XE. So this edge E is subdivided, and you call this guy like maybe call this a split node. Okay. Every edge you add a node. XE is a split node of E, and then you can define the set XE to be like all the split node in the graph G prime. Okay. So G prime contains like G prime would contain original nodes and all the split node. Okay. Now here's a better way, at least in my opinion, to think about expander. Now you can think of the clique, the unweighted clique, like the complete graph on XE. So think of KE is just for each XE, XE prime, XE prime prime, and so on. This form a clique. This is and this is unweighted. It's not just some product graph. It's complete unweighted graph. Okay. Now I will just state it actually, but we can prove it maybe. I will prove it tomorrow because I don't have time. But what we're gonna show is that a graph is an expander. Okay. G is an expander if and only if you can embed this the unweighted clique on split node. That is, you can embed the KE into the graph after you're splitting this edge. Okay. So you have a graph G, and you think of graph G prime. It's just better to think about G prime. And if this graph G prime, look at this graph G prime, and look at all the split nodes. If you can embed a clique between edges, between split node, then that graph is an expander. So let's just, you don't need to read this yet, but the thing that is that when you have a large conductance, what it really means is that every edge is well connected. Every edge in the graph, you can send flow between any, like, think of edge as a vertex itself, and every edge you can send all-to-all flow between them.
So these split nodes are standing for the edges, basically.
Yeah, split node is just like, think of it as an edge, yeah. So more formally, if a graph is a phi expander, then like you can embed a clique on split node. Like edges can send all-to-all flow to each other. By embedding a KE into G prime, it means that edges can send all-to-all flow in G prime with small congestion.